evening, everyone. My name is Hafiz Sheikh, and I'm the business head for Manufacturing Today magazine. On behalf of ITP Media, Manufacturing Today, Husky Injection Molding Systems, ladies and gentlemen, I welcome you all in today's webinar on a very interesting topic, how to succeed with bioresin for injection molding applications. Before we quickly jump to the session, let me just introduce ITP Media. ITP Media Group publish more than 100 weekly and monthly magazine with a large portfolio of digital and properties. We also organize 100 business and consumer events and conference globally. We have a large portfolio, which includes manufacturing, architect, construction, healthcare, media and broadcast, and many more. The platform which we are hosting today, Manufacturing Today, is India's leading magazine, which focuses on people, process, and technology for large and MSME. A partner who's supporting us today for the webinar is Husky Injection Molding, world leaders in injection molding systems. In the fast-paced world of technology changes, companies are expected to keep learning and unlearning new things, develop in order to stay ahead. Having the latest information and technological know-how ahead of others can change the course of your growth in the competitive world. In today's webinar, industry expert from Husky will provide an in-depth insight on how to succeed with bioresin for injection molding applications. A little about our partner today. Husky Technology is a leading industrial technology supplier to the plastic processing community. The company designs, manufactures, and services the industry most comprehensive range of injection molding equipments, including machines, mold, hot runners, auxiliaries, and integrated systems. With this, I would like to introduce our speaker for today, Sheldon Alexander, Hot Runner Business Manager at Husky Technologies. Sheldon has more than 20 years of global industry experience. He's traveled to the world to help optimize injection molding application. He's with us. So welcome, Sheldon. With this, I would like to hand over to Sheldon to share his insight on the topic today.
Good morning, good afternoon, guys. Just give me a second here to share my screen. Let's get going. So the topic for today is how to succeed with bioresins for injection molded applications. On the agenda today, the growing opportunity in bioresins, overview of commercially available bioresins on the market, bioresins challenges and best practices, bioresin application examples, and how Husky enables you to succeed with bioresins. So the growing opportunity in bioresins across a number of industries and applications, bioresins have become an increasingly popular alternative to the traditional resins used in injection molding. The global market for bioresins has risen steadily over a number of years and is expected to continue that growth at an impressive rate. Over the next 5 years, the market is expected to double in size. We're looking at 17% CAGR in the US market, and that's between 1920 and 1930, and about 13% CAGR in the European market. And again, that's between 2022 and 2027. For innovative brands and injection molders, this adds up to significant growth opportunities. What's driving the growth in bioresin adoption? First is the consumer. Consumers today want to know the product they purchase as well as their packaging as sustainable. Because bioresins are derived from relatively sustainable material and can be engineered to be biodegraded, many consumers feel bioresins are a healthier choice for the planet. The second is ESG initiatives. Brands and molders are under increasing pressure to adopt an ESG strategy. ESG stands for environmental, societal, and governance. It's a way of doing business. Using bioresins for injection molded products and packaging help organizations to meet their ESG objectives and signal to consumers that they're doing their part for the environment. And lastly, and probably the most important, there's legislation. So new legislation and regulations are placing pressure on manufacturers to reduce post-consumer waste and plastic pollution. For example, in July 2021, the European Commission implemented new laws that ban or restrict single-use products made from petroleum-based polymers those same legislation is happening all over the world as we speak. So an overview of some of the bioresins we have available. So bioresins, sometimes called bioplastics, biopolymers, or biomaterials, refers to several categories of commercially available material that can be used in the injection molding process. What makes bio-based is that they are made in whole or in part from renewable biological resources. These biological resources can include corn, tapioca starch, potato starch, vegetable oil starches, sugarcane, and wood pulp cellulose. The terms that's used in bioresins. When planning to use bioresins, it's important to note a few distinctions in the related terminology and features. Bioresin refers to the fact that biomaterials are used to create the resin. Biodegradable means the items will eventually break down in the natural environment. Not all bioresins are biodegradable. Compostable. So compostable means the material is biodegradable and breaks down within 3 to 6 months in an industrial composting facility, releasing valuable nutrients and leaving no toxicity in the soil. Not all bio-based and biodegradable resins are compostable. So I think this is an important slide, and I think I'm going to review those terms again because it's easily misunderstood in the industry today. So again, bio-based refers to the fact that biomaterial are used to create the resin. Biodegradable means the items will eventually break down in the natural environment, and not all bio-based resins are biodegradable. An important distinction. Compostable. Compostable means the material is biodegradable and breaks down within 3 to 6 months in an industrial composting facility, releasing valuable nutrients and leaving no toxicity in the soil. Not all bio-based and biodegradable resins are compostable. So an important distinction with those 3 different terms. So commercially available bioresins and what can they replace? So non-bioresins, we have things like linear low density polyethylene, high density polyethylene, polystyrene, and PET. Typically, those can be replaced with PLA. The raw material for PLA typically is corn starch or tapioca starch, and sometimes sugarcane. Polyethylene can be replaced with PHA or PHB. And again, that's corn, tapioca, potato, or vegetable oil based. And finally, polypropylene can be replaced with cellulose. Usually that's made from wood pulp. So those are the 3 main categories of standard resins and the bioresins that they can be replaced with. So a little more details. So PLA, again, it's the raw material are several different starches: corn, tapioca root, and sugarcane. The process by which it's derived, polyester is derived from renewable raw material sources. And as I mentioned, some of the resins that this can substitute is linear low density polyethylene, high density polyethylene, polystyrene, PET, and polypropylene. PHA is another one of these resins that's gaining popularity in the market, along with PHB. These could also be made from various starches, including corn, potato, maize, tapioca, and vegetable oil. The process of manufacturing PHA and PHB is quite unique. Polyester is derived from microorganisms through bacterial fermentation. And again, PHA, PHB is really good at replacing polypropylene and polyethylene applications. And finally, cellular base. Cellular base is basically wood pulp. It's a modified thermoplastics made from cellulose fibers, and it's good at replacing polypropylene. Some of the challenges and best practices when working with bioresins. So the first is material, and probably one of the most challenging fact of trying to run these applications So bioresins materials comes with unique and challenging physical properties that can make them difficult to incorporate into the injection molding process. For example, many bioresins are highly viscous, require high fill pressure to fill molded cavities, and they tend to be prone to leakage and weepage. Next is manufacturability. Some bioresins are very temperature sensitive. To avoid this, the manufacturing process must avoid exceeding temperatures above a certain threshold. This can pose challenges for systems that are not designed to meet these challenges of bioresins. Performance. So using new material brings a number of unknowns, especially in the area of performance. Many bioresins may not perform as well as traditional materials in terms of product preservation, longevity, safety, and other key performance criteria. These unknowns needs to be addressed in order to achieve a successful adoption of bioresin. And finally, quality. Quality is another area where bioresins may not initially meet the same standards as traditional material. Molten bioresin tends to be very corrosive, which can compromise equipment and lead to quality issues, performance variation, and even component failure. This may require more frequent equipment inspection and maintenance to ensure consistent and predictable uptime. So as I mentioned, corrosion is one of those challenges that we see out in the industry. And what I have here is some pictures of examples of corrosion. The first picture all the way to the left is a component in a hot runner system. It's a plug in the manifold, and you can see the corrosion on that. Second is a nozzle tip, and you can see the corrosion on that as well, also part of the hot runner system. And then the picture all the way on the right is a picture of a cavity or a core. And you can see the corrosion on that as well. So corrosion, as I mentioned, is one of the concerns with some bioresins. You have to take that into consideration when looking at the screw, the barrel, the steels used in the hot runner, as well as the mold itself. Some more examples of the challenges we see with bioresins. So leakage or weepage within the hot runner system itself is commonplace with these resins due to its corrosive nature, its viscosity, and its how easy it is to weep or to leak. So let's talk about some of the best practices for succeeding with bioresins. To avoid issues like we've seen in the last couple of slides, to be successful with bioresins, here are the key best practices taken from our extensive experience with this application. So one, we need to conduct an in-depth review of the application and the bioresin itself prior to any manufacturing step. Ensure the hot runner and controller are optimized for bioresin. This should include ensuring that the manifold design is optimized, ensuring consistent preparation of the bioresin, and we'll take a closer look at some of these in the next few slides. So optimizing the application or understanding the application to optimize the design. So we need to conduct an in-depth review of the application and bioresin itself prior to any manufacturing step. And this should include a cavity fill analysis. Again, as I mentioned, with the viscosity difference in bioresin compared to traditional resins, it's typically a lot more difficult to fill the cavity. So that needs to be taken into consideration, and a fill analysis will help with that. Evaluate the need for a resin test. So this is something we typically do at Husky, especially if it's a new version or a new bioresin that we haven't encountered before. We will request some resin into one of our labs and we'll do a resin test. This is usually recommended for resins with limited performance data or for particularly challenging applications. Evaluate the bioresins for any guidelines on maximum pressure. Review the low delta temperature between the tip and the gate, which could cause leakage issues, something we need to pay attention to. So specifically, how do we optimize the hot runner and controller? So we need to ensure that the hot runner and controller are optimized. This should include corrosive resistant components if the bioresin is corrosive in nature. Weepage mitigation components, again, because it's so easy to leak, so easy to weep, especially with a valve gate system. We need to make sure we take that into consideration and design accordingly. The type of gate, so a plunger gate that will give us the best possible gate quality. Individual tip control, improve heat distribution. Basically, we want the best possible thermal profile on that manifold so we don't have hot spots or cold spots that can lead to resin degradation. And an IO connection with the machine to avoid resin degradation. Basically, what that means is that we would recommend a controller that can interface with the machine so that if the machine goes down for a certain period of time, let's say 15 minutes, that controller can automatically bank the heats so that we're not degrading the resin. And again, I've mentioned corrosive resistance a couple times so far. With resins that is corrosive in nature, the more you degrade it, the more corrosive it gets, and it just dissolves all the steel around it. So certainly something you want to avoid. Continuing with optimizing the manifold design. So what we want to ensure is that the manifold design is optimized for bioresin. This should include geometrically balanced channels. Basically, the distance from the sprue bushing to each gate or to each part, whether it's a 2-drop or 144 drop system or 144 cavity system, we want to make sure that that channel length is the same, and that's what we refer to as geometrically balanced. Avoid bridging manifold heaters. So typically hot runner suppliers will have a heater on the injection side and another heater on the clamp side of the manifold. And many times we will bridge those heaters or connect those heaters together to have one thermocouple controlling both of those heaters. We would recommend not doing that to give you the better control of the thermals of the manifold. Melt channel size optimize for low pressure, reduce shear rates, and minimize the residence time. So this is something that the hot runner suppliers, we balance on every system that we build, trying to manage the pressure drop in the system, especially with bioresins, because of the viscosity, it has a tendency to lose a lot of pressure in the hot runner. So we want to take that into consideration. We want to make sure we have an optimal shear rate, so we're flushing those channels every shot. And we want to minimize residence time because of the thermal sensitivity of a lot of these resins in the industry today. Husky engineers each manifold's designed for the specific application and optimizes a balance between pressure drop, shear rate, and residence time. So some of the inputs we're looking for is resin. So we need to know what type of resin it is, the family, whether there's flame retardant, the additives or other additives, the specific grade, similar grades that might be available for us to do the analysis. So one of the things when you do a mold flow, if you don't have the resin characterized, you don't have the rheological data of that resin. So typically you're looking for a similar grade. Processing parameters. So we'd like to know the injection time or range of injection times that you intend to use, the melt and mold temperature, drop locations, part geometry, volume, thickness, ideally part file, so we can run analysis on the part itself, and performance requirements, cycle time. Are we doing color change? Are we looking for specific balance requirements? So those are all the inputs, and the output to that is a melt channel layout, melt channel diameter, just optimizes the geometry of the manifold. System performance, so it gives us what the predicted pressure drop is, the shear rate within the melt channels, the shear rate at the gate, the temperature increase as a result of that shear rate. So as the resin is flowing through the hot runner, it's picking up heat as a result of that shear rate. We want to know what that temperature increase is. Specifically, we want to make sure we keep it under under the limits set forth by the resin supplier, so we're not degrading the resin. And then finally, residence time. Residence time is simply how many shots you have in the melt channels of the hot runner system. Next is thermal uniformity. So what we want to do with thermal uniformity is Husky performs a FEA, or a thermal finite element analysis, which gives us a good indication of what the manifold temperature variation is going to be based on the specific design. By adjusting that design, by adjusting the heater wrap, the number of heater zones, thermocouple placement, melt channel layout, heat sinks, and manifold profile, the designer can optimize that thermal uniformity of the system prior to releasing it to manufacturing, again, using finite element analysis, or FEA, to help with that process. Husky performs FEAs on almost all of our designs. And this is something we've been doing since 2013. Almost all of our hot runners are designed this way, and it's allows us to confirm that the design is optimized and gives us the best possible thermal profile. That includes plate cooling, waterline routing on the plates, both the manifold plates and the backing plate. So number 4, ensuring consistent preparation of the bioresin. This should include adequate drying before use. So many of the bioresins available on the market is hydroscopic, and very hydroscopic as that. We're looking at moisture content to be less than 250 parts per million, and that's required to prevent degradation. Bioresins are typically supplied in foil-lined boxes or bags dried to less than 400 parts per million. The resin should not be exposed to atmospheric condition until it's absolutely necessary, and then it should go directly into the dryer and molded. Every minute that bag is open, it's absorbing moisture. So you want to reduce that or prevent that as much as possible. As I mentioned, keeping that package sealed until ready to use is the best practice. Next, we have some application examples that we have running in the field right now with some of the bioresins available on the market. So this is a fork application. We've done quite a bit of cutlery over the last, I would say, 15 to 20 years. PLA is one of the first bioresins that were available in the market. It has this specific application. We're looking at a 4.6 gram part weight, about 1.25 millimeter thickness, and this was a 32 drop valve gate system. System ran with no issues. Another PLA application, this was a family tool. So customers mold in all three, knife, fork, spoon at the same time. Another PLA application with MFI of 35, 6 grams, 1.25 millimeter wall thickness, and this was a 48 cavity or a 48 drop valve gated system. Coffee capsules or K-cups, so disposable coffee pods is something that we've done quite a bit of. This is another PLA application, 2.9 grams. Fairly thin wall thickness, if you've felt any of these parts. So they're about 0.15 millimeter thick. And this was also a 48 cavity valve gated system. Another coffee capsule example, also PLA, 5 grams, 0.6 millimeter wall thickness. And this was a 4 drop valve gated hot runner system. This was an interesting one. So this is a cellulose or a wood pulp based resin, fairly heavy part at 15.42 grams, wall thickness between 0.6 and 0.8. And this was a 1 drop system. So customer just did a prototype on this system. System ran pretty good with this specific resin. Another cup application with PLA, 2.2 gram, 0.8 millimeter thick, and this was a 4 cavity or a 4 drop system. This one here, a customer ran several different resins, a PHA, a PLA, with two different PLAs, two different manufacturers, three different part weights, so 14.97 gram, 16.35, and 14.72, about 0.6 to 0.8 wall thickness, and this was also a single cavity. We do resin trials, as I mentioned, in our lab, specifically for resins that we haven't encountered before. We have several test tools that we use. One of them is a Petri dish tool, and we ran this specific resin on this 2-cavity Petri dish tool at Husky. So it's a PLA plus wood. So it wasn't cellulose, it wasn't wood pulp, it was just wood chips that was mixed into the PLA. A 6.7 gram part, 1 millimeter wall thickness. And again, this was a two cavity or a 2-drop system. We were able to make acceptable parts for the customer. Same tool, running a cellulose-based resin, 6 gram part. And we were able to be successful with the resin and then move on to the production tool with the customer. This was another trial that we did, 4.8 gram part. So the core on this mold is adjustable, which allows us to change the wall thickness, which in turn changes the part weight to try and mimic the specific application that the customer is trying to run. So again, these are resin trials that we did with a Husky tool to confirm that the resin is processable, to learn as much as we can before we design the production system. Another Petri dish application, 5.1 gram part, no issues with this resin as well. So how does Husky enable you to succeed with technology, without our specific technology, our experience, and our expertise in the area? Husky offers the right combination of experience, expertise, and technology to ensure successful adoption of bioresins for your application. It takes all three to get it right. So as I mentioned, a lot of the resins on the market, a lot of the bioresins on the market is very corrosive. PLA, I would say, is probably the most widely used resin in the market, and PLA is extremely corrosive. As such, we've created a unique line of hardeners where we needed to change the steel of all the components that touches plastic. So we offer a complete system solution, ideal for the successful adoption of bioresins into your injection molding operation. Our UltraMelt hardener is the key component of that. UltraMelt is engineered for applications requiring excellent process and thermal control with minimal effects on the resin chemistry. This specific hardener features 100% non-reactive surfaces and or steel components to preserve the sensitive chemistry of the bioresin, minimizing corrosion and other challenges. With the UltraMelt, the melt path is protected. So from the sprue bushing to the manifold bushing, the valve stem, the nozzle housing, the nozzle tip. So as I said, every component that touches plastic is either stainless steel or a non-reactive coating to be able to protect that steel and that hardener to last you a very long time. So we can go into questions that the group might have now. I'll pass it back to the moderator for questions.
Hi, Sheldon. Really appreciate you. Thank you very much. Yes, we have a question. People, while registration, people have sent question, and I'm sure you'll be very kind enough. You have been shared a lot of information, but also do answer this question. So the first one, I'll take it. Have you seen an increase in bioresin usage? How does it impact HR maintenance interval?
Yeah, so we have seen a tremendous increase in bioresin inquiries, opportunities, and sales in the last 2 years. As I think everybody realizes, the world is changing very quickly when it comes to plastics. Everybody's looking for an alternative to what's in the market now, whether that's biodegradable, compostable, or any of those other categories. So yes, we do see a tremendous growth in that industry. As far as hot runner maintenance goes with bioresins, as I mentioned, bioresins do have some unique characteristics that challenges hot runners compared to conventional resins on the market. So it's corrosiveness is one. We need to take care not just of the hot runner, but of the machine, the injection unit, the screw, the barrel, and as well as the molds. So you want to make sure you're using the right steels, that's corrosive resistance, or coatings that's corrosive resistance as well, to give you the best start with the system. So that's one. Two, having strong PM procedures, just good manufacturing practices. So you're cleaning the vents regularly, you're performing PM on the hot runner regularly. Any leakage that might occur, any weepage that might occur, especially with a valve gate system, you want to clean that up. You don't want it to degrade, because as I mentioned, as it degrades, it becomes even more corrosive, wears components, and then that gives you, whether it's leakage in the hot runner or flash in the mold. Hopefully that answers that question.
Yeah, you talk about height, hot runners and corrosive. That's the second question we have from the audience is, what experience do you have with high temperatures or corrosive resin? And what is the different compared to bioresin?
So we have quite a bit of experience with both high temperature and corrosive resins. So we run high temperature resins like polysulfone, PEEK, that runs above 800-900 degrees Fahrenheit. So we have quite a bit of experience with high temperature. Same with corrosiveness. Flame retardant is an additive that's added to conventional resin quite a bit. Plastic components that is in high heat environment or need UV stabilizers. There's a lot of flame retardant in there, and flame retardant itself is extremely corrosive. So from those two avenues, we have quite a bit of experience, and we're able to move some of that experience over to bioresins and over to that ultra melt specific hot runner that I mentioned that is able to withstand the unique properties of the bioresins and available in the market right now.
Can you provide some specific example of a good use of bioresin?
So I would say any single-use plastic item today is probably the best use case. So knives, forks, spoons, coffee capsules, replace straws, plates, any single-use item, consumer item are good examples of applications that can benefit. Packaging equipment as well. That's something we don't usually think about, and that is the ultimate in single-use item, right? You buy something in the store, you take it out of the packaging, you throw it away. You don't even use it, right? So that's another good example, I think, of making a difference.
The next one, can a traditional hot runner system be upgraded or revised to accommodate a switch to bioresin if the original system was for the different resin?
Yeah, that's a good question. What I tell customers in cases like that is, if you have an existing work cell, meaning you have a mold, you have a hot runner, you have a machine that you're running polypropylene, and you want to try a bioresin, go ahead and try it. You already have the system, check with the hot runner supplier, make sure that the delta T's, the temperatures are not outside of what it was originally designed for. On a typical Husky system, that shouldn't be a problem. Short term, no concern with trying it on a conventional system. Long term, that's a different story. If the hot runner was not designed with corrosive resistance and the bioresin you're using is corrosive, then long term that's not going to work. There is things we do unique to bioresins for weepage, for leakage as well, that might not work in the long term with a standard conventional system, but in the short term, no problem.
The next one is, what are the Husky's capabilities for testing new bioresin?
So we have labs with a lot of machines in many locations globally. So in the US, in Milton, Vermont, in Europe and Africa, Luxembourg. We also have lab in 2 locations in China. So we can test almost any resin available on the market. Usually we need about 50 kg, depending on the application. We will work with the customer to figure out what's the best mold. We have upwards of 100 molds in our inventory, and we will pick a mold similar enough to the application that the customer is looking at to be able to get a good comparison with that specific resin.
Thank you, Sheldon. You've been very kind enough to share the inputs. Now we have a very quick survey, and would request everyone to please do share your feedback. It's very important for us. And from our side, from Manufacturing Today, get a 1-year free subscription of the magazine. Here's the question. Please, you'll be getting 30 seconds to choose one. Please do respond and get a chance to get a 1-year free subscription. I can read the question based on the information in this webinar. Do you feel you have a better understanding of the benefit of hot runners? Single sets, yes or no. So maybe we'll wait for a minute or so to show the result of that. And Sheldon, I would also request, based on the result, you share your feedback. You've been very kind enough to share your the technology, the insights of the industry.
Yeah, wonderful response on the first question. Second question, among the benefits of a hot runner system might bring you, which is considered to be the most critical to your production, improve part quality or reduce scrap rate? Absolutely. A hot runner can go a long way in improving both of those, scrap rate and improved part quality, specific gate quality, process window. That all makes sense, and increase uptime. Yeah, I think those would be the responses we would expect. Thank you, guys.
Thank you very much. With this, we come to an end of the very interesting webinar. Thank you very much. With this, we conclude this webinar, and I would like to say a big thank to Sheldon for joining us today and sharing the insight, which is much needed in today's market. The session was filled with insight. Sheldon, thank you again for sharing your real-time experiences. We appreciate the dedication in sharing insight in the interest of the industry, and also the audience. Thought-provoking questions from audience made the discussion lively. We hope it was a learning experience for each stakeholders of the summit. With this, we end this session. Thank you very much for your time. Be safe.